So here we're going to work an example using the conservation of energy equation that we developed using the Reynolds transport theorem. We are given a compressor, and it's just a generic compressor. We don't have to worry too much about the specific geometry of it, which makes these problems a little bit easier. There's no angles or vector triangles we have to worry about. And air is entering the compressor at port 1 and leaving at port 2 with the conditions as shown. It's entering at atmospheric, P1 equals 14.7 psi absolute. We're going to use absolutes because we're going to end up using ideal gas equations here in a bit. V1 is essentially 0, so we're going to be able to ignore that. And the temperature at the inlet is a nice comfortable 70 degrees Fahrenheit, which works out to about, 540 Rankine. Oops, 530 Rankine. Sorry about that. At the outlet, we're told that the pressure, P2, is equal to 50 psi absolute, and that the temperature is equal to 100 degrees Fahrenheit, which is going to be equal to 560 degrees Rankine. We're told that the area at the outlet, we'll call it A2, is equal to 1 square foot. The airflow rate, the mass flow rate through the compressor is 20 pounds mass per second, and the power into the compressor, we'll call it W dot shaft, is equal to 600 horsepower. Our job is to find the rate of heat transfer. And we'll call it Q dot from the compressor, to or from the compressor. I guess we should say to the compressor. And then if it ends up being negative, we'll know that it's actually coming from the compressor. So we're going to make a number of standard assumptions. We're going to assume steady flow inside the compressor. We're going to assume uniform flow across the inlet and the outlet. We're going to treat the gas as an ideal gas. We're going to assume that the velocities are perpendicular to the inlet and the outlet, perpendicular to the control surface of the inlet and outlet. We're going to ignore changes in elevation, and we're going to ignore the kinetic energy or the velocity coming in at the inlet. So the first thing we're going to do, of course, is draw our control volume around the compressor like that. And so we know that the only control surfaces where anything is actually crossing any air is crossing our control, our boundary, are given by the solid red lines. And then of course there is shaft work being done and heat being input into the system, where again we're expecting Q dot to be negative, but by convention we draw a positive Q dot as going into the system.